Deep beneath dry salt flats and rocky terrain, the journey of a phone battery begins in a way that feels almost unreal. Lithium, a soft, silvery metal, is so light that it can be cut with a simple kitchen knife. But what makes it truly powerful isn't how it looks, it's what it can do. Lithium has an unusually high energy density, meaning it can store a large amount of energy in a very small space. That single property is the reason modern smartphones can last all day on something that fits in a pocket. And while there are other elements that can theoretically store more energy, they're either too rare or too impractical to use at scale. Lithium, on the other hand, is relatively abundant. That balance between performance and availability is what made it the backbone of modern batteries. But lithium doesn't come ready to use. It has to be extracted, refined, transformed, and engineered with extreme precision before it ever powers a device. From salt water beneath the earth. One of the most common ways lithium is obtained doesn't involve traditional mining at all. Instead, it starts with something unexpected: underground salt water. In regions like Chile and Argentina, vast reserves of lithium-rich brine sit hundreds of meters below the surface. This brine is essentially highly concentrated salt water, often several times saltier than seawater. To access it, wells are drilled deep into the ground, the hard rock route. Not all lithium comes from brine. In places like Australia, lithium is found locked inside solid rock, primarily in a mineral called spodumene. Extracting lithium from this source is a far more mechanical and energy-intensive process. It begins with blasting. Large sections of rock are broken apart using explosives and heavy machinery. Once extracted, the ore is crushed and ground down into a fine powder. But even then, the lithium isn't ready. The powdered material is heated in massive industrial kilns at temperatures exceeding 1,800 degrees Fahrenheit. This process, known as calcination, drives off unwanted components and transforms the mineral into a form that can be chemically processed. After heating, the material undergoes further chemical treatment to produce a lithium-rich solution. This solution is then filtered and refined until it becomes lithium hydroxide, a key ingredient in battery production. What started as solid rock is now a fine powder or crystalline compound, ready to enter the next stage of its journey, from chemical to component. At this point, lithium has been extracted and refined, but it still isn't a battery. Inside manufacturing facilities, this lithium compound is combined with other materials to create what will eventually become the heart of a battery cell. Once prepared, the slurry is carefully applied onto extremely thin metal foils. Copper is used for one side of the battery, while aluminum is used for the other. The coating process has to be incredibly precise. Even small inconsistencies can affect performance, lifespan, or safety. After coating, the sheets pass through long drying chambers. These can stretch dozens of meters, and their purpose is simple but essential: remove all excess moisture. Moisture inside a battery is dangerous. It can lead to contamination, degradation, or even failure. So this step ensures that only the intended materials remain. Building the battery's core. Once dried, the coated sheets are cut into long strips. These strips are then rolled together in a tightly packed spiral structure, often referred to as a jelly roll. This design isn't random. By rolling the materials together, manufacturers maximize the surface area inside a compact space. More surface area means better electrical interaction, which translates to higher capacity and improved efficiency. The jelly roll is then inserted into a protective casing, forming the basic structure of a battery cell. At this stage, the battery is starting to take shape, sealing, structuring, and preparing for life. Inside the cell housing, the internal layers are carefully aligned and compressed. This ensures durability and consistent performance. The structure needs to withstand physical stress, temperature changes, and repeated charging cycles. Every detail matters. Once assembled, the cell is sealed to prevent contamination and protect the internal chemistry. But before it can power anything, there's one final transformation left. The first charge. Newly assembled battery cells don't come pre-activated. They go through a process known as formation, essentially their first charge. During this stage, the cell is charged for the first time under controlled conditions. This step stabilizes the internal chemistry and prepares the battery for real-world use. At the same time, the cell's performance is carefully evaluated. Technicians test its capacity, monitor how it charges and discharges, and check for any irregularities. Cells that don't meet strict standards are removed and replaced. Only the ones that pass every test move forward. Not just one battery, but many. A single battery cell isn't always enough, especially for larger devices, so multiple cells are combined. Before assembly, each cell is cleaned using advanced techniques like plasma treatment. This removes microscopic impurities that could interfere with performance. Then, cells are stacked or arranged together in a way that balances power, size, and efficiency. The goal is to create a system that delivers maximum performance without adding unnecessary weight or bulk. These grouped cells form modules, and multiple modules come together to create a complete battery pack. Precision at every step. Inside these packs, every component has a purpose. Electrodes and separators are carefully positioned to maintain proper spacing and prevent short circuits. Heat management is also a major factor, as excessive heat can reduce performance or damage the battery. Connections between cells are welded to ensure strong electrical flow and structural stability. These connections are then tested to guarantee reliability. On top of that, systems are installed to manage how the battery operates, monitoring voltage, battery temperature, and overall health. Everything is designed to work together seamlessly. By this stage, what started as underground saltwater or solid rock has been transformed into a highly engineered energy system. But there's still more to the story, because turning a battery into something that safely powers a phone, day after day, requires even more layers of engineering, testing, and intelligent design. And that's where the process gets even more interesting. By the time individual battery cells are formed and tested, they're already capable of storing energy. But on their own, they're still incomplete. What turns these cells into something reliable enough for everyday use inside a phone is the way they are combined, controlled, and protected. Because a modern smartphone battery isn't just about storing energy, it's about delivering it safely, consistently, and efficiently, thousands of times over its lifespan. From cells to a unified power system, each battery cell that passed testing moves into the next stage, integration. Cells are grouped together and arranged in precise configurations. The way they are connected determines how much voltage and capacity the final battery will have. Some are connected in series to increase voltage, while others are arranged in parallel to increase total energy storage. This combination allows manufacturers to fine-tune performance based on the device's needs. Once arranged, these cells are assembled into modules. A module acts as a single unit, even though it contains multiple cells working together, keeping everything in balance. Inside a battery, balance is everything. Each cell must operate within a safe range of voltage and temperature. If one cell behaves differently, it can affect the entire system. To manage this, a specialized system is added, often referred to as the battery management system. This system continuously monitors the battery's condition. It tracks how much charge each cell holds, how quickly energy is flowing, and how temperature changes during use. If something goes outside safe limits, the system steps in. It can reduce power, adjust charging speed, or in extreme cases, shut the battery down entirely to prevent damage. This invisible layer of control is what allows a phone battery to function reliably without the user ever noticing the complexity behind it. Cleaning at the microscopic level. Before final assembly, there's one more step that might seem almost excessive, but it's essential. The surfaces of the battery components are cleaned using plasma. This isn't ordinary cleaning. It involves exposing materials to a high-energy environment filled with charged particles. These particles remove microscopic contaminants like organic residues or metal oxides that could interfere with performance. Even tiny impurities can reduce efficiency or create instability over time. So this step ensures that every surface inside the battery is as clean and reactive as possible. Designing for efficiency and safety. Inside the battery pack, components are arranged with extreme care. Electrodes and separators are positioned in a way that minimizes resistance while preventing short circuits. Heat dissipation is also carefully considered, since excessive heat can degrade performance and shorten the battery's lifespan. The internal layout isn't random. It's engineered to maintain harmony between electrical performance and thermal stability. Every millimeter matters. Final assembly and protection. Once modules are complete, they are placed into a protective housing. This housing is designed based on the device it will power. In smartphones, space is extremely limited, so the battery must be compact, while still delivering enough energy for all-day use. The testing before it reaches your pocket. Before any battery is approved for use, it goes through a series of rigorous tests. These tests evaluate how the battery performs under different conditions. Charging speed is measured. Discharge rates are analyzed. Capacity is verified to ensure it meets specifications. But testing doesn't stop there. Batteries are also checked for durability, how they handle repeated charging cycles, temperature variations, and physical stress. Any unit that fails to meet the required standards is removed. Only the batteries that pass every test move forward to be installed into devices. How energy actually moves inside your phone. Now comes the part that often goes unnoticed. What happens when the battery is actually in use? Inside the battery, energy isn't stored as electricity in the traditional sense. It's stored chemically. When the phone is in use, lithium ions move between two sides of the battery. As they move, they create a flow of electrons through the phone's circuitry. That flow is what powers everything, from the screen lighting up to apps running in the background. When the phone is plugged in, the process reverses. Energy from the charger pushes the lithium ions back to their original position, storing energy again for later use. This constant back and forth movement is what allows a battery to be recharged hundreds or even thousands of times. Efficiency beyond charging. In larger systems like electric vehicles, there's an additional concept called regenerative braking, where energy is recovered during deceleration and fed back into the battery. While smartphones don't use regenerative braking, the idea highlights something important. Modern battery systems are not just about storing energy. They're about managing it intelligently. Every bit of energy is tracked, controlled, and optimized to get the most out of a limited space, from raw material to everyday power. What started as underground brine or solid rock has now become a compact, high-performance energy system. It has gone through extraction, purification, chemical transformation, precision manufacturing, and rigorous testing. Every step was designed to ensure one thing: reliability. Because once inside a phone, the battery is expected to work flawlessly. It powers communication, entertainment, navigation, and countless daily tasks. all without drawing attention to itself. And yet behind that simplicity lies one of the most complex manufacturing processes in modern technology. From salt flats and mineral-rich rock to ultra-thin layers of engineered materials, the journey of a phone battery is anything but simple. It's a process that blends chemistry, engineering, and precision manufacturing at every stage. And the result is something that feels almost invisible, a small, lightweight component that quietly powers modern life. If this breakdown gave a new perspective on something used every day, consider subscribing for more deep dives into how everyday technology is actually made. There's always more happening behind the scenes than it seems.